Welcome to this walkthrough of LeetCode problem number 459, repeated substring pattern. In this session, we'll explore how to determine if a given string can be formed by repeating a proper substring multiple times. Let's dive into the problem and break it down step by step. The problem we are tackling is called repeated substring pattern. The goal is to determine if a given string can be formed by repeatedly appending a smaller substring. A substring is simply a contiguous block of characters found within the string. To solve this problem, we are given a non-empty string S. The task is to check if this string can be constructed by taking a smaller substring and replicating it multiple times. The output will be a Boolean value, true if the string can indeed be formed this way, or false if it cannot. Let's consider an example to understand this better. If the input string is S equals ABAB, we need to determine if a smaller substring can be repeated to form this entire string. In this example, the output is true. This is because the substring AB can be repeated twice to recreate the original string ABAB. Now, take a look at another case where the input string is S equals ABA. Here, the output is false. The string ABA cannot be constructed by repeating any smaller substring. There is no pattern or block of characters that can be appended multiple times to recreate ABA. These examples highlight the kind of reasoning we need to apply when solving the problem. Now consider the input string S equals abcap. In this case, the output is true. The substring ABC can be repeated 4 times to form the string abcap. This demonstrates how longer strings can also be tested for repetition patterns. On the other hand, if the input string is a single character, such as S equals A, the output is false. Since there is no smaller substring to repeat, a single character string cannot satisfy the repetition condition. To summarize, if the input string consists of just one character, like A, it is impossible to construct it by repeating a smaller substring. The constraints for this problem specify that the length of the string can range from 1 to 10,000 characters, and it will only include lowercase English letters. Efficient solutions are crucial due to the potential size of the input. Some edge cases to consider include strings like AA, where the entire string is a repetition of A, or strings like ABCD, where no valid substring exists to construct the entire string. Additionally, for very large strings, it's important to ensure the solution can handle the input size efficiently without compromising correctness. To solve the problem of determining if a string can be constructed by repeating a substring, we first consider a brute force approach. The idea here is straightforward. We systematically check all possible substring lengths from 1 to half the length of the string. For each candidate length, we determine if the string can be evenly divided into parts of that length. If not, we skip it. But if the length is valid, we extract the substring and check if repeatedly concatenating it reconstructs the original string. While this method is simple to understand and implement, it comes with a trade-off. Since we have to check multiple substring lengths and validate each by reconstructing the string, the time complexity can grow to n squared, in the worst case. This makes the approach computationally expensive, especially for larger strings. However, it provides a clear and systematic way to explore the problem initially. A more efficient solution involves a clever insight about the nature of repeating substrings. If a string is formed by repeating a substring, then it must appear as a proper substring within the concatenation of the string itself. Here's how it works: we create a new string by doubling the original one, and then we remove the first and last characters of this doubled string to avoid including the original string directly. Once modified, we simply check if the original string exists as a substring within this new structure. This eliminates the need for manual checks of substring lengths and repetition. The beauty of this approach lies in its efficiency. With the help of efficient substring search algorithms, the time complexity is reduced to n. The trade-off here is that the insight about string doubling might not be immediately obvious, but once understood, it leads to a quick and elegant solution. Another strategy leverages mathematical properties of divisors. If the string can be formed by repeating a substring, then the length of this substring must be a divisor of the string's total length. Using this idea, we calculate all divisors of the string's length, excluding the length itself since it would represent the entire string. For each divisor, we extract a candidate substring and check if repeating it the appropriate number of times reconstructs the string. This method is more efficient than brute force because the number of divisors is proportional to the square root of the length, reducing the number of candidates we need to test. The overall complexity is O(n*(sqrt(n), as verifying each candidate substring requires O(n). While this approach is faster than the brute force method, it still involves explicit substring checks, making it slightly slower than the optimized string manipulation strategy. The chosen strategy for solving this problem is the optimized string manipulation approach, which relies on the insight that if the string is formed by repeating a substring, it will appear as a proper substring within its doubled version. This realization is the key to the solution, as it eliminates the need for time-consuming substring extraction and comparison. With a time complexity of O(n), this method is not only the fastest but also the simplest to implement. However, it does require a conceptual understanding of the string doubling principle, which might not be immediately intuitive to all learners. We opted against the brute force approach due to its inefficiency for larger strings and the divisors method because, while faster than brute force, it still involves iterative checks that add computational overhead. Ultimately, the pattern doubling method strikes the ideal balance between efficiency, simplicity, and elegance, making it the optimal choice for solving this problem. The goal of this problem is to determine if a given string can be formed by taking a smaller substring and repeating it multiple times. For instance, the string ABAB can be constructed by repeating the substring AB twice, but the string ABA does not have such a repeated pattern. To start with, we can approach this problem using a brute force method. Here, the idea is to test all possible lengths of substrings, ranging from 1 to half the length of the string. Why only up to half the length? Because a substring longer than half the string cannot repeat enough times to form the entire string. For each potential length, we first check if the length of the string is divisible by the substring length. If not, it cannot evenly divide the string, and we skip it. If it is divisible, we extract the substring and then repeat it enough times to match the original string length. This can be achieved through string multiplication. If the repeated version matches the input string, we return true, as we have found a valid repeated pattern. If no valid substring is found after testing all possible lengths, we return false. This approach systematically checks all possibilities, but as we'll see, it can be optimized further. To make the solution more efficient, we can use an optimized approach based on string manipulation. Instead of explicitly testing all substrings, we manipulate the string in a way that avoids the need for nested loops. First, we create a new string by concatenating the input string with itself, resulting in a longer string. Then, we remove the first and last characters of this concatenated string. This ensures that any valid repeated substring pattern will appear as a contiguous substring within this modified string. The key insight here is that if the input string can indeed be formed by repeating a substring, it will naturally show up as a substring in this manipulated version. This is due to the overlap of the repeated structure when we double the string. Finally, we simply check if the original string exists as a substring in this modified version. If it does, we return true. Otherwise, we return false. This approach eliminates the need to explicitly construct and test each possible substring, making it significantly faster. In terms of computational complexity, the brute force approach can take up to O(n)² in the worst case, but this optimized method reduces it to O(n), as it relies on efficient string operations. The optimized approach achieves its efficiency by leveraging string concatenation and substring search, both of which operate in linear time. This results in an overall time complexity of O(n). Additionally, this method manipulates the input string directly without requiring any additional data structures. Temporary strings are used in both approaches, but the optimized method avoids unnecessary computations. Now, let's consider some edge cases. For instance, a single character string like a cannot be repeated to form itself, so the output should be false. Similarly, strings like ABC, which do not exhibit any repeated patterns, should also return false. On the other hand, strings like AAA or ABAB must correctly identify their repeated patterns and return true. An empty string, although not explicitly mentioned in the problem, should logically return false since there's no valid substring to repeat. To better understand how these approaches work, let's step through a few examples. Take the string ABAB as an example. Using the brute force method, we first test substrings of length 1. Repeating a 4 times gives AAAA, which does not match ABAB. Next, we test substrings of length 2, extracting AB and repeating it twice. This gives ABAB, which matches the input, so we return true. In the optimized approach, we concatenate ABAB with itself to get ABABAB. After removing the first and last characters, we are left with BABABA. Checking if ABAB is a substring of BABABA, we find that it is, so we return true. Now consider a string like ABC. The brute force approach finds that no substring length produces a valid repeated pattern, and the optimized method confirms this, as ABC does not appear as a substring in the manipulated version of itself. For the final implementation, the optimized solution can be written concisely in Python. By doubling the string, removing the first and last characters, and checking for the substring, we achieve an efficient solution. This is the essence of how we solve the problem using both the brute force and optimized approaches. This code solves LeetCode problem 459, repeated substring pattern. The goal is to determine whether the string S can be formed by repeating one of its substrings multiple times. We begin by calculating the length of the string S and iterating through all possible lengths for a potential substring, from 1 to n/2. This range is chosen because any substring longer than half the string cannot repeat to form the full string. For each possible substring length, we first check if it evenly divides the length of the string. This ensures that the string can be evenly split into repeated parts of that length. If the length is valid, we extract the substring of this length from the beginning of the string. Next, we construct a new string by repeating this substring enough times to match the length of S. If the constructed string equals the original string, we return true immediately, indicating that S can indeed be formed by repeating this substring. If no such substring is found after checking all possible lengths, we return false at the end, indicating that S cannot be formed by repeating any substring. This approach efficiently checks all possibilities while avoiding unnecessary computations, and it ensures correctness by thoroughly verifying each candidate substring. Here, we are implementing the solution to check if a given string can be formed by repeating a substring. First, we determine the length of the string, n. Then, we iterate through all possible lengths of the substring, starting from 1 up to n/2 because a repeated pattern cannot have a length greater than half the string. For each potential substring length, we check if it evenly divides the total length of the string using the modulus operator. If it does, this means the string could potentially be composed of this repeated substring. We then extract the substring from the start of the string using s.substring 0 length, and create a new string by repeating this substring enough times to match the original string's length. This is done using a string builder and a loop, where the substring is appended repeatedly n/length times. After constructing the repeated string, we compare it to the original string. If it matches, we return true, indicating the string can indeed be formed by repeating this substring. If none of the possible substring lengths result in a match, the method will exit the loop and return false, indicating that the string cannot be constructed by repeating any of its substrings. This completes the implementation. By systematically checking all valid substring lengths and constructing potential repeated patterns, we ensure that the solution is both efficient and thorough in identifying whether the input string meets the criteria. Here, we begin with an example where the input string is ABAB. The length of the string is 4. To determine if this string can be formed by repeating a substring, we loop through all possible substring lengths up to half the length of the string. In the first iteration, we consider a substring length of 1. Since 4 is divisible by 1, we proceed to extract the first character, which is a. We then construct a repeated string by multiplying this substring by the quotient of the division, resulting in AAAA. However, when we compare this constructed string to the original, they do not match. Therefore, we continue checking with the next possible substring length. In the second iteration, we check for a substring length of 2. Since 4 is divisible by 2, we extract the first 2 characters, which gives us AB. Using this substring, we construct a repeated string by multiplying it by 2, resulting in ABAB. This time, when we compare the constructed string to the original, they match exactly. This means the string ABAB can indeed be formed by repeating the substring AB. As a result, we return true, indicating that the input satisfies the condition of the problem. Next, we consider another example where the input string is AAA. The length of the string is 4. Again, we loop through possible substring lengths. Starting with a length of 1, we check if 4 is divisible by 1, which it is. We extract the first character and construct the repeated string by multiplying this character by 4, giving us AAA. Comparing this constructed string to the original, they match. Since we found a valid repeated substring in the first iteration, we immediately return true. In this example, the input string is ABCD, and its length is also 4. We begin by testing a substring length of 1. Since 4 is divisible by 1, we extract the first character and construct the repeated string by multiplying it by 4, resulting in AAA. However, when we compare this constructed string to the original, they do not match. This indicates that a substring of length 1 cannot form the original string, so we proceed to check the next possible substring length. In the second iteration, we consider a substring length of 2. Since 4 is divisible by 2, we extract the first two characters, UB, and construct the repeated string by multiplying this substring by 2, resulting in ABAB. Comparing this constructed string to the original, they do not match either. As we've now exhausted all possible substring lengths up to half the length of the string and found no valid repetitions, we conclude that the input string ABCD cannot be formed by repeating a substring. Therefore, we return false. To summarize, the algorithm systematically tests all possible substring lengths, checking divisibility, extracting substrings, and validating against the original string. It returns true if a match is found and false otherwise. To analyze the time complexity of this solution, we start by examining the outer loop, which iterates over possible substring lengths from 1 to n divided by 2. In the worst case, this results in n divided by 2 iterations, which is O, n. Within each iteration, there are several operations to consider. First, the divisibility check to see if n is divisible by the current length is a constant time operation, O1. Next, creating a substring using slicing, s length, takes O length time since it generates a new substring of that size. Then, we have string multiplication, where we repeat the substring enough times to match the length of the original string. This process takes O n time because the resulting string is proportional to the size of the input string, s. Finally, the comparison of the repeated string to the original string also takes O n time, as it involves comparing two strings of the same length. These steps form the building blocks of our time complexity analysis. Now, let's calculate the total time complexity for each iteration. The most significant contributors to complexity within each loop are substring creation at O length, string multiplication at O n, and string comparison at O n. When combined, the total time per iteration simplifies to O length plus n, which is dominated by O n, since n is typically much larger than the substring length in these scenarios. Moving on to the overall time complexity, the outer loop runs O n iterations, and each iteration involves operations with a dominant cost of O n. As a result, the total time complexity becomes O n multiplied by O n, giving us O n squared as the final time complexity for this solution. Shifting our focus to space complexity, the memory usage is primarily influenced by two operations. First, creating a substring, s length, requires allocating memory proportional to the substring size, which can be up to n divided by 2 in the worst case. However, this memory is reused across iterations and does not accumulate. Second, string multiplication generates a new string, repeated, with a size equal to the input string, s, which is O n. This memory is also reused in each iteration. Since no additional data structures are used, the auxiliary space remains constant at O1. In total, the space complexity is dominated by the repeated string, resulting in an overall space complexity of O n. When comparing the current approach to a naive solution, the differences in efficiency become clear. A brute force method would involve checking all possible substrings of all possible lengths, concatenating these substrings repeatedly, and comparing them to the original string. This approach would require iterating over all substrings and performing repeated operations, leading to a time complexity of O n cubed. In contrast, the current solution narrows down the possibilities by only considering substring lengths that evenly divide n and directly constructs the repeated strings for comparison. This optimization reduces the time complexity to O(n squared). As for space complexity, both approaches require O(n) space due to the creation of the repeated string. Additionally, the best-case scenario occurs when a pattern is found early, such as when the string is highly repetitive. This results in a time complexity of O(n). On average, the function will iterate partway through the loop, maintaining O(n squared) complexity. In the worst case, where no repeated pattern exists, all iterations are completed, and the time complexity remains O(n squared). To mathematically validate the big O complexity, we note that the outer loop executes up to O(n) times, iterating over substring lengths up to n divided by 2. Within each iteration, the dominant operations, such as string multiplication and comparison, contribute O(n) to the complexity. Combining these, we multiply O(n) for the loop with O(n) for the iteration cost, resulting in O(n squared) as the total time complexity. For space complexity, the primary factor is the size of the repeated string, which is proportional to the input string and requires O(n) memory. Thus, the overall space complexity is O(n), confirming our earlier analysis. One of the most common mistakes in solving the repeated substring pattern problem is assuming that the substring must always be contiguous or of a specific length. The truth is, the substring can be of any length, as long as it repeats to form the entire string. Overlooking this flexibility often leads to incorrect solutions. Another frequent pitfall is failing to account for edge cases, such as single-character strings or empty strings. It's important to remember that these are valid inputs, and not handling them explicitly can cause runtime errors or unexpected results. Lastly, many beginners try to generate all possible substrings explicitly and check each one, which is highly inefficient. This approach can lead to time complexities as high as O(n squared), or worse, making it impractical for larger inputs. Instead, focusing on optimized methods is key to solving this problem efficiently. Another common mistake is ignoring modular arithmetic when testing substring lengths. For a substring to repeat and form the entire string, its length must divide the total length of the string evenly. If the length of the string is not divisible by the length of the substring, it's a clear indication that the substring cannot satisfy the problem's requirements, and any further checks on it are redundant. Additionally, some solutions fail to validate the reconstructed string. Just because a substring has a valid length doesn't mean it's automatically correct. You must ensure that repeating this substring the appropriate number of times actually reconstructs the original string. This validation step is crucial for avoiding false positives and ensuring the accuracy of your solution. To solve this problem effectively, it's important to focus on key insights. First, recognizing that the problem involves the mathematical properties of string repetition is critical. For instance, if the string can be expressed as a substring repeated k times, then the length of the string must be divisible by the length of the substring. Optimal approaches often leverage string manipulation techniques, such as the double string trick. By checking whether the string appears in the middle of its own concatenated version, excluding the first and last characters, you can solve the problem efficiently. It's also essential to test edge cases, such as single-character strings, strings with prime lengths, or strings made entirely of the same character. During interviews, make sure to explain the trade-offs of different approaches. While brute force methods are intuitive, they are inefficient for larger inputs, whereas mathematical or string-based solutions are faster and more elegant. This problem is closely related to several other LeetCode challenges. For example, LeetCode 28, Implement strstr, focuses on substring search and shares similarities in its foundational concepts. LeetCode 686, Repeated String Match, involves determining how many times a string must be repeated to contain another string, which is another variation involving repetition. LeetCode 796, Rotate String, tests whether one string is a rotation of another, highlighting advanced string manipulation techniques. Finally, LeetCode 1044, Longest Duplicate Substring, delves into efficient substring searching using advanced algorithms like suffix arrays. Exploring these related problems can deepen your understanding of string operations. When considering alternative approaches to solving the repeated substring pattern problem, brute force is simple to implement but inefficient, as it involves explicitly checking all possible substrings. On the other hand, mathematical approaches, such as modular arithmetic, are faster but require additional steps to validate the reconstructed string. Balancing simplicity and efficiency is key when choosing the best method. One of the most efficient methods for solving this problem is the double string trick. By concatenating the string with itself and checking if the original string appears within the modified string, excluding the first and last characters, you can quickly determine if the string is composed of repeated substrings. This approach is highly efficient with a time complexity of O(n), but it may be less intuitive for some to derive in an interview setting. Another advanced option is the Knuth-Morris-Pratt, or KMP, algorithm. This method identifies the longest prefix of the string that is also a suffix, providing insights into the string's repetitive structure. While the KMP algorithm is optimal for larger strings, it requires a deeper understanding of string algorithms and pre-processing steps. Mastering these techniques not only helps in solving this problem efficiently but also demonstrates strong algorithmic thinking and string manipulation skills. That's it for this problem. Today, we explored an efficient way to solve the repeated substring pattern problem using string manipulation techniques. Remember to apply these concepts to similar challenges and keep practicing. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!